So, good evening. Today we will start with the designing of the infinite impulse response filters. So, what is the difference between FIR filters and IIR filters? We have already discussed. So, I am moving forward. So, if you look into the equations of an FIR filter, if you see, we have Hz equals to 1 plus B Z inverse plus C into Z minus to the power minus 2 plus D Z to the power minus 3 and so on. So we had like this. So if we multiply both the numerator and denominator with Z cube, which is the highest power of the Z inverse, so we get this equation, and from here we see that all the poles they are at the center, and from the numerator if we solve it we will get the placement of the zeros. So if you look into the transfer function of FIR filter, it was quite simplistic in nature. Okay. On the other hand, when we consider IIR filter, in the IIR filter, what happens? So we will get two types of polynomials, YZ and XZ. So both of them they would be polynomial. So herein, if you see 1 plus B Z inverse divided by 1 plus A Z inverse plus A Z to the power minus 2, then if we want to find out the locations of the poles and the zeros, we need to multiply and divide with the z square, which is the highest power over here of the z to the power minus 1. Okay, so it's in the denominator. So when we do that, we will be getting two polynomials, and after getting those two polynomials, we can find out the placement of the poles and the zeros. Now, if we proceed with the simplification of this transfer function itself, so we get yz multiplied by this thing, okay, it goes over there, and this xz it goes to the numerator on the right hand side. Okay, so if you do that, we get this equation, and taking yz on the left hand side and taking all the xz and yz's on the right hand side, we get this equation. Now if you look over here, what happens is that if you look, we are having xz multiplied by z inverse component, we have yz into z to the power minus 1 component, we have yz into z to the power minus 2 component. Okay, so what does this imply to us? What does this imply to us? So if you consider the FIR filters, so what happens in the FIR filters? The output was dependent on the present input and the past inputs. Okay, the output was dependent on the present input and the past inputs. On the other hand, if you look into this equation, what does this signify? This signifies that the output, it is dependent on the present and past inputs. Apart from this, we are having the outputs of the previous instances that are also taken into account to calculate the present output. So that means output of an IIR filter, they are not only dependent on the present and the past inputs, but they are also dependent on the past outputs. And this is what we mean by the feedback systems. So the past outputs, they are considered to calculate the present outputs. Okay. So we have also discussed, if you are given with the Z transform equations, how we can get into the differential equation by applying the inverse Z transform. Okay. Now let us take an example. So what is the example? The example is hz equals to 1 by 1 minus a z inverse. Okay. Now this is the transfer function. Okay. This is the transfer function. Now if you want to find out the location of the poles and the zeros, so what you will be having? So z divided by z minus a. So where is the 0? 0 is at the origin. And where is our pole? Pole is at equal to a. A comma 0 कहाँ से आ गया? It's only a z, no, z equals to a. Okay, so now what happens if we have a equals to 0.5, a equals to 1, a equals to 1.5. So if you look into the pole zero plot, if I draw it separately, if a is equal to 0.5, it should be here. Okay, so it is stable. If a equals to 1, it should be on the unit circle, and if a is equal to 1.5, it should be outside the unit circle. Okay, now if you look, we have implemented or realize the filter, and after the realization of the filter, if we want to find out the transfer function hn for when a is equal to 0.5, a equals to 1, and a equals to 1.5. Okay, so in the first case, if you see, our output due to an impulse input would be 1, 0.5, 0.25, 0.125, and so on. So if you look into the response, it is dying down as the time progresses. So we can say at time tending to infinity, our impulse response value will be tending to 0. Okay, so from there we can say that the filter what we have designed is a stable filter. Okay, now consider a equals to 1. So when we give an impulse input, we get yz, which is equal to 1 1 1 1, and it continues up to infinity. Okay, now since it continues up to infinity, what happens? The coefficients, they are neither going out of bound nor they are dying down. Okay, so due to this reason, this filter, it would be regarded as no, neither stable nor unstable filter, or we can say marginally stable filter. Okay, we can say marginally stable filter. Lastly, if we have a equals to 1.5, so which is outside the unit circle, if you see the output values, it would be 1, 1.5, 2.25, 3.375, and so on. So if you see, it is continuously increasing. And since it is continuously increasing, that means at t tending to infinity, our hn value would be tending to infinity. That means the system is unstable in nature. So the system would be regarded as Bibo unstable system. Okay. Now coming to the IIR filter designing methods. So what are the different IIR filter designing methods? The first one is the impulse invariant method. Second is the bilinear transform method. Third is the frequency transformation method. And lastly, we have the approximation of derivatives method. Okay. Now, yeah, one important thing I forgot to mention. So if you consider this equation, this transfer function, how do you implement it? The implementation, it has been given over here. So if you see, we are taking the output values and it is going into an adder. Okay, so that is giving us the feedback loop. So this is nothing but your feedback loop. Okay, so yeah, now coming back to the impulse invariant method, today we will be discussing about the impulse invariant method. So it is the most simplest method for designing IIR filter. Okay, so impulse invariant method, the placement of the poles and zeros in the Z plane, they are basically the if we get the information from the X plane, so we take that information and we just put it into the Z plane just by a simple mapping. So how do you do the mapping? So 1 by S minus P1, that means the location Pi is the location of the pole. So this is being mapped into 1 by 1 minus e to the power Pi T Z inverse. Okay. So the location of the pole over here is S equal to Pi, and over here in the digital domain it would be Z equals to e to the power Pi T. How this is coming? Because Here we are having z inverse. So if you multiply both numerator and denominator with z, so you get z equal z minus e to the power pit. So if you equate it, so the location of the pole is this one, right? Now, if you see, S is also given by sigma 1 plus j omega 1, and this omega, it is nothing but your analog frequency. On the other hand, this z is equal to e to the power st, where s is again sigma 1 plus j omega 1 t. Okay. Now this comes out to be e to the power sigma 1 t multiplied by e to the power j omega 1 t. Okay. So modulus of z, it is nothing but e to the power sigma 1 t, and phase of z, it is equal to omega 1 t. Okay. Now if sigma 1, it is less than 0, that is we are in the left hand side of the plane. So if you put less than 0, so it would be within the unit circle of the z plane. Similarly, when sigma 1 is equal to 0, we are on the frequency axis in the s plane. So on, and in the z plane we will be on the unit circle, which is the frequency component. Similarly, when sigma 1 is greater than 0, we will be outside the uh, this unit circle, right? Now if you see, if your analog filter, it is stable in nature, that means your digital filter will also be stable in nature. Okay, because all the criteria of a stable filters, they are being met. Okay, they are being met. So that's what it has been told over here. If we are starting with a stable analog filter, if we use the impulse invariance method, we will be getting a stable digital filter also. Okay. However, there are certain problems over there. So why the problem comes? The problem comes because in this method, we are having many to one mapping. Now, what do you mean by many to one mapping? So let us start with this derivation to understand the thing better. So Z is equal to R into e to the power j omega. We have seen from the previous slide. Also, Z is equal to e to the power st. So R into e to the power j omega is equal to e to the power sigma t plus j omega t. Right? Now R is equal to e to the power sigma t, and omega is equal to this omega t, where this omega, it is the analog frequency. So omega is equal to digital frequency by capital T. Okay. So the time period of the samples. Okay. Now if you look over here, our analog frequency, it is equal to, it is directly proportional to the digital frequency. Okay, it is directly proportional to the digital frequency. Now the thing is that our analog frequency, it can vary from minus infinity to infinity. However, in the case of digital frequency, it is bound within 0 to 2 pi. And if you go beyond 0 to 2 pi, what will happen? It will be repeating on to itself. Similarly, if you go below 0, that means you go to the negative digital frequencies, again it will be within on the this unit circle itself. So that means what happens in the unit circle, one particular point, it is corresponding to multiple analog frequency components. Okay, it is corresponding to multiple analog frequency components, and due to this reason we call this mapping as the many to one mapping. Okay, and this will lead to the overlapping of the frequency components when we design the IIR filters using the impulse invariance method. Now, when there is overlapping of the frequency components, what we discussed? We discussed that it is nothing but aliasing. Okay, it is nothing but the aliasing. So, one of the major problem with this kind of filter systems where the digital filters are being designed using impulse invariance method is the aliasing. Okay. So because of this reason, when we are trying to develop any filter by this method, the analog frequency has to be properly band limited. Has to be properly band limited. Okay. So we have to limit the frequency components within the signal. Okay. So the first one what we discussed is for the distinct poles. Okay. Then there are other parameters where there are multiple poles or the complex poles, then in those cases these other three equations they come into play. Okay. Now let us take an example. So hs equals to 1 by s square plus 5s plus 6. Okay. Now this can be broken down as s plus 2 multiplied by s plus 3. Now if you try to break this equation through partial fraction, you get a by s plus 2 divided plus of b by s plus 3. You break it down by the partial fraction method, a by s plus 2 plus b by s plus 3. Then you find out the values of a and b, and it comes out to be 1 and minus 1. So from here you find out the equation. So our equation is 1 by s minus p1. So we have to convert it into this form, s minus of 2 minus of 1 by s minus of 3. Then we have to apply the transformation. So when we are applying the transformation, we would assume if nothing is given, then we will assume that the time period it is equal to 1 second for our convenience. So if you see, we are just using this equation and getting the value. E to the power minus pi is minus of 2 capital T z inverse and so on. So t is equal to 1 second. So once you do this, you get this one. Then you solve it, and after solving, you get this transfer function. So after that, you can find out the what do you call this realizes the filter, and also find out the amplitude and the phase responses. Okay. Similarly, over here also we get the same thing, 2 by s square plus 8s plus 15. Okay. So over here, then h is equal to this thing. By partial fraction method you do the breaking, and then you solve it. Okay. Now if t is given, t is equal to 0.2 seconds. So in many cases, what happens is that this capital T is equal to 0.2 seconds. We are applying a multiplication factor capital T, and these are usually for the high sampling rates. So anything less than 1 second, you can blindly apply this transfer function. Okay, this multiplier T. Okay, the rest of the method it remains the same. So again over here, this impulse invariance method, you break it down by the partial fraction method, apply all the things, and if you see whatever the values you will be applying, you need to keep in mind that it is in radians. Okay. Now if you look over here, this a plus uh, if you consider it as capital A divided by 1 minus a to the power some factor t z inverse plus a divided by 1 minus a to the power some factor c, if you consider is small a plus jb, here it is a minus jb. So in this format we are having. So if you go back over here, if you get the things, you will be getting in this fashion. Okay. S plus a divided by s plus a whole square plus b square. So this equation it would be applied. Okay. So once you do this, so what happens is that You solve it, and after solving you get this equation. Now I have already told that for sampling period t, uh, the sampling period t scales the impulse response because the discrete impulse response values are sampled at intervals of capital T. So the overall amplitude needs to be adjusted according to the approximate the continuous analog response accurately in the digital domain. Okay. So these are the differences between the different methods. Okay. So if you look into the impulse invariance method, it converts analog filters to digital by sampling the impulse response of the analog filter. Okay. Simple to implement, maintains exact correspondence with the analog impulse, the response at the sampling rate. Okay. Then disadvantages, aliasing can occur if the analog filter has high frequency components that exceed half the sampling rate. Application suitable for low pass filters where aliasing is less problematic. Okay. So the bilinear transform method, frequency transform method, and the approximation of the derivatives we will be discussing as we go towards the next thing. All of this just uh, we have discussed today. Okay. So all of this I have included so that you can uh, write it down in your examination. Okay. So everything I have already discussed. So what are the steps? We have already looked into the numericals, and this is the thing what you need to perform the steps just for your yeah, easy remembrance. The same thing. Okay. So when you will be using, when you will not be using. Okay. So another important thing, when you will be using, usually this T factor it is being used when there is high sampling rate. Uh, Usually when sampling frequency is greater than equal to 10 of f of max. Usually we have this Nyquist rate of fs equal to nearly equal to 2 of f of max. But if it is more than that, then we usually apply this T multiplier. Okay. So anything we need to discuss? It is just by putting the same values, the first method itself. Okay. This is the first method itself. Here I have not included the other examples. Again, I am reminding you, whenever you are doing these numericals, you need to keep in mind that when there is cos and all these things, these should be in radians. Okay, be careful with that while doing the numericals. So first of all, you do this, find out the impulse response when is equal to 0.5, 1, 1.5. Try to implement and do this.